Hi there, welcome to my channel. In this video, I'm going to explain about the solution for calculating x raised to the power n. Let's look at the problem description. We have to implement a function which calculates the x raised to the power n. Okay, so let's take a look at the example 1. So the input is 2.0 and exponent is 10. So 2 to the power 10 is 1024. So in the case of example 2, the base number is 2.1. The exponent is 3. So 2.1 power 3 is 9.261. Okay. So in the case of example 3, base number is 2.0 and the exponent is negative. Okay. So the 2 to the power minus 2 is equal to the reciprocal of base number 2 raised to 2. So in that case, the reciprocal of 2 is 1 by 2 is 0.5. And 0.5 times 0.5, it is 0.25. So the constraint for this problem are the value of x is ranging from minus 100 to 100 and the exponent value is ranging from minus 2 to the power 31 to 2 to the power 31 minus 1 and n is an integer. Either x is not 0 or n is greater than 0. The output will be in the range from minus 10,000 to 10,000. Let's look at the approach to solve this problem. So the input given is the base number is 2.0 and the exponent is n is 10. So the expected output will be 1024. Brute force approach to calculate the x raised to the power n is by multiplying the number x repeatedly with itself n minus 1 time. So this works for the smaller value of n. As per the problem description, the highest value possible for n is 2 to the power 31 minus 1. It's 2.1 billion. If the exponent value is at the higher end, then we will do the multiplication 2 billion times with the floating point inputs. Okay, so that is inefficient. So another approach to compute the exponentiation is using the binary exponentiation technique. Basically, this is a technique to compute x raised to the power n using log n number of multiplications. X raised to the power n is defined as follows. If the value of n is equal to 0, then the output is 1. So if the exponent is even, then x raised to the power n is equal to the square of the base number raised to the power n by 2. Basically, the base number will be squared and the exponent will be halved. Okay, if the exponent number is odd, then x raised to the power n is equal to the square of x raised to the power n minus 1 by 2. For example, in the case if x is 3 and n is 8, the binary representation of the 8 is 1000. So the log 8 is 3. We can compute the x raised to the power n with 3 multiplications. First, we have the value x is equal to 3 and n is equal to 8. Okay, as per this formula, x is not equal to 0. Okay, so then we square this, so 3 to the power 2 and then we halve the exponent value, so it becomes 4. So here the value of x is 9 and the exponent will be reduced to 4. And in the next step, the base value x is squared and the exponent is halved. So here x is equal to 81, here n is equal to 2. And in the next step, the 81 is squared and raised to the power 1. And here the value of x will become 6561 and the value of n will be 1. In the next step, this will be 0. Then finally, we get this output as the 3 raised to the power 8. So that's what I have written here. First, we initialize the result variable to 1. And then if the power is less than 0, then we have to convert that into a positive number by multiplying that number by minus 1. And then we have to update the x with the reciprocal of the x, 1 divided by x. Then we write the for loop to perform the multiplication log n number of times. Okay, so basically we perform the calculation based on this definition in this for loop. So if the n is odd number, then we assign the product of the result and the variable x to the result variable. Then we decrement the n. Regardless of the n is odd or even, we have to square the x and then we halving the exponent. We repeat this until n is equal to 0. Then finally we return the result. Let's look at the flowchart. Input for this procedure is base number x and the exponent n. Okay. First we initialize the result to 1 and then next we check whether the exponent is equal to 0. So anything raised to the power 0 is 1. So we simply return with the result value 1. Okay. Otherwise we check whether the exponent is negative. In that case we make that as positive by multiplying that by -1 and then update the value of x by its reciprocal 1 divided by x. Okay. Then we enter this for loop. Okay. So each iteration we check whether n is greater than 0. If that is true, we check whether that number is, the exponent is an odd number. If it is an odd number, we decrement the exponent and then multiply the result with the value of x and assign the product back to the variable result. Okay. If it is an even number, we don't have to do this. And then in each iteration, we update the value of x by squaring it and we update the value of n by halving it. When the value of n is equal to 0, then we break out of this loop and then finally return the result. Let's move on to coding. First I check whether the value of n is equal to 0. If that is true, I return 1. Next I check whether the value of n is less than 0. In that case I make the value of n to be positive by multiplying with -1 and then I update the value of x with its reciprocal 1 divided by x. Next I initialize the result variable with value 1. Then I write the for loop. This will run until n becomes 0. First I check whether the n is an odd number. If that is true, then I update the value of result by multiplying the result with the variable x. Then I decrement the value of the exponent n. Next I update the variable x with its square. Next I update the value of n with its halved value, n by 2. Finally I return the result. Next I am going to run the test cases. All the tests passed. Next I am going to submit this program. Cool, this program is accepted. Next I am going to do the code walkthrough with sample input. So the input given is the base number x is equal to 3 and the exponent n is 8. The expected output is 6561. Okay. First we check whether the exponent is equal to 0. In this case it is not. So we go ahead and check whether the exponent is negative. In this case the exponent is positive. So we go ahead and initialize the result variable with value 1.0. Then we enter this for loop. Each iteration we check whether the exponent is not equal to 0. In this case it is not equal to 0. Then we go ahead and check whether the exponent is an odd number. In this case, it is an even number, so we do not update the result variable. Instead, we update the variable x by squaring it. So that's why x becomes 9, and then we having the exponent. So that's why the exponent value will be changed from 8 to 4. And in the iteration 1, the value of x is 9 and the exponent is 4. N is not a odd number. Again, we square the x and halve the exponent. So the 9 times 9, 81, and the exponent will become 2. Okay. And in the next iteration, again n is not equal to 0, and then we go ahead and check whether it is an odd number. In this case, it is an even number. So we go ahead and square the current value of x and assign it back to x. So now x is assigned with 6561, and we have the exponent value. N will be changed from 2 to 1. Okay. And in the next iteration, we check whether the n is an odd number. In this case, it is an odd number. So we update the result variable by multiplying the result with the variable x. So the result is 1 and the value of x is 6561. So the value of the result variable will be 6561. Then we square the value of x and then have the exponent. So in this case, the exponent value will become 0. Then in the next iteration, because n is equal to 0, we break out of this for loop and finally return the result. So the result contains 6561. That is an expected output. Next, I am going to do the time and space complexity analysis for this solution. The time complexity of this procedure is order of log n, where n is the value of the exponent. Okay. Let's take a look at the case 1, where the base value is 3 and the exponent is 8. Okay. So let's see how many iterations this for loop performs. As per the code walkthrough, we saw that this for loop performs 3 iterations. The log 8 is 3. In the case of 2, the exponent is 64. In this case, this for loop will run for 6 iterations. Okay. Log 64 base 2 is 6. If the value of the exponent is n, then this for loop performs log n number of iterations. So that's why the time complexity of this procedure is order of log n. Okay. And the space complexity is order of 1 because no additional space used in this procedure. We just use only one variable to store the result. So that's why the space complexity is order of 1. Thanks for watching this video. Have a great day.